Okay, welcome back. We keep going with the afternoon session on cosmic dawn and JWST. The next speaker is Rychard Bouwens, and he will talk to us about ALMA and JWST view of massive galaxies at redshift 7.
Okay, so it's a pleasure to be here. There's been a lot of great talks, a lot of great discussions so far at this meeting, and yeah, it's always great to be back in Santa Cruz. So I'm going to be talking about the Rebels program, a significant sample of galaxies at redshift 7, and talking about ALMA and what you can learn from ALMA and JWST. So there's a lot of people that have basically been helpful for the preparation of the material. Some of the people here in particular have been very helpful for, in some of the material I'm going to be showing today. I'd like to particularly highlight some of the names here who have essentially been students and postdocs in recent years. So a lot of this stuff is actually being done by the young people that have been through Leiden over the last many years. So it's a lot of things you'll see from that. I'm going to be talking about some basically follow-up results, mostly from, and also some results as well from the main survey from the Rebels program, the reionization era bright emission line survey. It was a cycle 7 large program. I was the PI of it, and there was a bunch of great co-Is and co-PIs. I think Andrea Ferrara is here from that team, and he's contributed a lot to this as well as many other people. One of the aims of the survey was basically to try to understand how massive galaxies assemble in the early universe. How is the mass growth in metals and dust related to the buildup of gas and stars? And basically learning things about the kinematics and how this could impact the growth of these objects. So a lot of great things here, and JWST's only continued to build on a lot of this. Our sample was basically taken of a lot of very bright galaxies. We identified from very wide area observations over fields like Cosmos, XMM, basically a 6 or 7 square degree area. And we looked for some of the most robust objects and brightest objects of that field, and then we targeted them for spectral scans and targeted with ALMA. So we basically targeted the very bright high redshift component. The survey worked out pretty well. Basically, we've gotten data in cycle 7 and cycle 8. We have basically around 25, depending where you set the threshold, 5.2 sigma C+ lines identified in those 2 years. Here are some of the 7 sigma lines that were identified in cycle 7. You can see they're very high significance. Here are some of the sources in cycle 8. Basically, some of this stuff is still in preparation. It's been taking the students some time to get to that. They're very smart, but sometimes just finishing things is a little more challenging. So there's a lot of great things in this survey. We found, again, large numbers of lines. There's a huge variety of different morphologies of these sources, both in terms of the C+ emission, which traces a neutral gas, the dust emission, which traces obscured star formation, and the unobscured star formation, which you can see from the UV. So there's a large variety of different things. Some sources show dust emission, some just show more C+. There's sometimes dust offsets between the C+ and the emission and the UV emission, and all sorts of different things. So there's a huge variety of different morphologies in these samples, also in terms of the width of the lines, etc. And so basically, to really try to make sense of what we're seeing with these samples, the sample of massive galaxies, we really wanted to bring in JWST. With ALMA, you have a lot of things like these things, cold gas kinematics, dust content, but we'd really like to bring in things like the ionized gas properties, stellar mass, metallicity, and get other things about the star formation rate. And so basically, fortunately, we had this program approved. Mauro Stefanon was the PI, was doing a lot of work in the trenches on the last day, trying to get it into a final form. We worked really hard on it together, and fortunately, it was approved. A lot of the sources have star formation rates of slightly in excess of 100 solar masses a year to maybe around 1,000 solar masses a year. And they're kind of in this regime between redshift 6.5 to roughly 8. The higher redshift sources, we've sometimes detected them, but for the most part, our bulk of our sample has been in this range, and that's where we've gotten most of our data. And we targeted 12 massive galaxies with ALMA-derived C+ redshifts, and we got some time to do that. We tried to pick objects which were representative of the bright galaxy samples, both in terms of IR luminosities, O3 equivalent widths, UV slopes, IR luminosities, et cetera, at stellar mass. And we targeted them with the IFU prism with just 30-minute exposures. It's amazing what you can do in 30 minutes. We now have data for 3 sources with 2 more targets to be observed this week. The prism can give us data with R of 100 to basically, once you get to the very red end, it's closer to maybe R of 300 resolution spectra for these sources in a single shot, which is just amazing data. And so basically, we got data for all these sources shown in red here. So we particularly at the very high star formation end, we tried to get some sources. And here are some of the objects that we've gotten data on so far. Here's the C+ lines and what we had with C+, far infrared continuum, and UV light for these sources. This is what we had before JWST. Now with JWST, we get these remarkable spectra. This is just 30 minutes, amazingly. And we have basically, signals noise in some cases seems to be almost of 100 for some of these lines. Basically, so with the redshifts, the 2 sources we targeted between redshift 6.6 and 6.8. The metallicities we're getting are fairly high, starting to be close to solar, depending on what metallicity measurement calibration you use or which lines. The dust exchange is fairly high. Star formations are modest, and the stellar masses we're getting are fairly modest. It's interesting to compare this with what we had in our proposal. I think obviously things are looking a lot better than in our proposal. We should have tried a little bit harder to sell this in our proposal, but the data is actually kind of amazing. Here's results for the other source. Amazing, we also even detect the O2 line and the sulfur 2 lines. Those are detected very high significance, and those aren't always detected in a lot of even much longer integrations with JADES. So we're getting information on these sources. And amazingly, we can easily separate the O3 doublet. So it's remarkable what we can do with these things. Again, a lot of these things very relatively high metallicities. And then what we've been doing is we essentially from these data sets we have spatially resolved maps of the cold gas, warm ionized gas, star formation rate, stellar mass, and dust. And we're still in the very beginning stages of starting to look at this and thinking about putting together papers. But basically, we have maps of not only the C+ and the dust. We have maps of the ionized gas. And we've been, just to start out, we've been comparing things like the Baumer decrement with the dust contours and comparing essentially these crude metallicity maps with the dust contours. And what we find is that basically the dust continuum tends to originate from the same regions where there's a peak in the Baumer decrement, which is encouraging, and also it seems to coincide with the highest ionization regions. Again, there's a huge number of papers that we sketched out that we may want to write on this, as many as 15 or so. And this just shows you basically the O3 to O2 map. And again, it seems to be fairly similar than if you use O3 over H beta. Here's for another source, basically at redshift 6.633. In this case, we don't detect, at least in the Rebels data, the dust continuum. So it's a bit of a different source than the other source. We have multiple components in this source. And what we've been doing is essentially starting to compare things like the Baumer decrement, the dust contours. And we're trying to look at a lot of these things like metallicity, Baumer decrement in a spatial resolved manner to try to make sense of actually what's going on, what dust law may be present, et cetera. And ultimately, again, we want to start looking at energy balance analysis of the whole the whole SED. Again, this is just a lot of this is I showed some of this earlier, but we're now just starting to dive into it and do things. So clumpier morphology, dust continuum emission. It's not prominent in the Rebels data. The peak Baumer decrement in this case does not seem to match the ionization peak. So again, some of these things need to be sorted out. Fortunately, we're getting data on many more sources. So there's a lot of source-to-source variation. While the dust continuum is not detected in our data, this is detected in some data that Rebecca Bowler obtained, and it actually has a fairly similar morphology to what we see in terms of the JWST data. And data sets. So we've also got data. We just got data on Friday for another source showing line maps of all these different lines. Basically, you can also get many things, R23, the H-alpha equivalent width, effectively, the Balmer decrement. So there's a lot of different things that we have on these sources. And these are apparently even higher signal to noise than the first two targets. Mauro just sent me this morning. But a lot of this stuff, we need to really dive into it. So one thing we're doing is sitting there, we've been looking at in a spatially resolved way where things land on the BPD diagram. And I don't know if we have a consistent interpretation yet, but what we're finding is that, so for example, this source, we have the yellow, this is magenta and green, yellow, magenta, and green. So they're landing in slightly, distinct parts of the diagram. We've also looking at this in a spatially resolved way. Again, they're consistent with lower redshift galaxies in terms of where they land on this diagram, consistent with somewhat higher metallicity, higher ionization. And so the ionization properties are basically, there's a slight difference between the inner and outer region, and this might indicate some redshift or mass evolution. We've also been comparing some of these galaxies with sources seen with Sears. This was the analysis by Ryan Sanders, and our sources tend to be basically shifted to the right of some of these other sources, basically consistent with our sources being much higher metallicity than other sources. So we've been pursuing a lot of different analyses on this. One of the questions is how does the stellar mass in these objects assemble? So we've been trying to look at extending the mass metallicity and the fundamental metallicity relations into a higher regime. And so if you look at where the mass and metallicity, our sources are predominantly landing way up here, which tends to be higher than what's seen in most of these analyses, essentially all the Jades and Sears samples. And we're also trying to look at the formation of dust at higher redshift. So we're hoping to, after we get our first set of papers done, finally start to look at things like the dust-to-gas ratio, the dust-to-metal ratio in these objects, so we can really try to get a handle on how dust builds up. A lot of these, as exciting as many of these early JWST results are, most of these samples don't have detected dust emission. So it's really be interesting to try to connect the buildup of metals and gas to the buildup of dust. Okay, so in addition to everything else, in addition to all these data sets, there's also NERCAM data available over these fields, thanks to programs like Primer and Cosmos Web. And so this just shows you for this source here. So we're starting to fill in this diagram even more to sort of exploit the ALMA+JWST synergy. And this, you can see that this is a much higher signal-to-noise version of what we previously had from the ground. Also, on a related note, it's useful to know that in addition to the Rebel sample having lots of very cool data on having very cool ALMA+JWST data, there's also very interesting data available for the crystal sample, which is another very massive sample of galaxies, but is between redshift 4 and 6, so a slightly different point in cosmic time. But then there's amazing data from this, both from Cosmos Web and from the crystal program, which obtained really very high spatial resolution ALMA observations. And again, this is just this is basically, they have a bunch of papers in prep, and this is just a nice montage of a lot of the C+ profiles of the 19 massive sources that they've collected data from ALMA over the last year and a half. Okay, so another thing you can do with these samples is also look at the kinematics. So let me just quickly show you some work on the kinematics. Because we have very high signal noise C+ lines in Rebels, for example, we can actually look at their kinematics, and analyze what's there. Basically, and if you look, and here are some of the kinematic profiles showing the line of sight velocity, and some work in preparation. Roughly half of the sources seem to be rotation dominated, seem to be dispersion dominated, but again, this is in preparation. In addition to all this, we can actually look at these things at much higher spatial resolution. And so we have a lot of follow-up programs, mostly led by Renske Smit, Jackie Hodge. I think one of them program was led by Manuel Aravina, which this is some work by, I think, a student or a postdoc in in Santiago. But yeah, so some of the sources in some of these data sets are, well, actually 3 of the 4 that we've looked at in detail are rotation dominated. One seems to be more dispersion dominated. Again, some of these things are still in preparation. I'll show you a little bit in more slide to follow. We have 4 more targets which we have data, which is analysis ongoing again by Sean Phillips at Liverpool. And we have 2 more sources which are approved. So we're following up on a lot of these analyses we've done at low spatial resolution by essentially looking at this much higher spatial resolution to really characterize the gas motions in these sources. Here's just a very detailed analysis done by Lucy Rowland, who's in Leiden. She's trying to get this paper finished before the data become public. This shows you the ALMA C+ contours gas. The orange shows you the dust contours. This shows you the gas kinematics map. Amazingly, this seems to be very consistent with simple rotation, simple disk rotation. This source was targeted because it was essentially the highest star formation rate source in Rebels, and it's basically consistent with being a ULIRG, and it's at redshift 7.3. So amazingly, what the source shows is that the V over sigma is around 5, which seems to be far in excess of what is expected in many of the different models. And in fact, the source doesn't seem to be that unusual. There's a lot of sources in these surveys which are showing very high V over sigma. So it's not completely clear what's going on. There's some theoretical models that would suggest this may become more common at high masses. We also have a lot of follow-up observations looking at other lines like the O3 line. From this, here are some line detections of this. This line largely originates from H2 regions surrounding star formation in galaxies, and it's thought to probe the ionization parameter. UC-HiPACC has a number of several papers discussing this, along with Akio Inoue. But we've been detecting this line, and we're getting slightly lower ratios for this. So we're finding that, particularly in the more massive regime, this ratio tends to be depressed. There's also been some very nice work done by Yoshi Fudamoto in basically going after the O1 line, has been able to detect the O1 line in a large number of different sources. I think we have at least 4 detections already using this line. This line is good because it's a nice tracer of the neutral gas in galaxies, and the ratio of this with C+ is a tracer of the neutral gas density. And what we're finding is that this ratio seems to be very enhanced, suggesting that basically there's a lot of neutral gas in these sources. Okay, sure. Okay, so then in addition to all this, we're also getting continuum detections and a lot of the follow-up data, it's giving us very high spatial resolution imaging of what these things look like in the far infrared continuum. They also give us information on the overall SED of the far infrared dust continuum. And so this allows us to measure dust temperatures and emissivities, and more importantly, estimate the bolometric luminosity and obscured star formation rates in these things. You need to know the shape of the SED to be able to actually estimate the total star formation or emissivity. If you only have one point, you can't really estimate the total area under the curve, but if you have multiple points, you can estimate the shape better, and then basically get the total star formation rates. This is important because the star formation rate can essentially depend on T dust to the 6th power. So here's some results from Rebels. There's a bunch of other results. Amazingly, at high redshift, there's a huge amount of scatter in this, so we need a lot more observations mapping out the shape of the dust continuum, given the huge amount of variance at high redshift. With Rebels, there's also, we've been trying to constrain the far infrared luminosity function, obscured star formation rate density at high redshift. So based upon the volume limited survey, where we've looked for Rebels galaxies and looking at the ratio of the UV to IR emission and the scatter in that relation, we've estimated IR luminosity functions, and in a variety of ways tried to translate that into basically constraints on the star formation rate density at high redshift. These are some of the constraints we came up with, which are fairly similar, a little bit higher than what Jorge Zavala came up with basically maybe a year prior. I mean, I think there's potentially very significant differences in the shape of the far infrared luminosity function, so that's going to obviously require some work to get to the bottom of. But there's obviously very exciting things going on here. Perhaps a more exciting way to try to more robust way to go about doing this is either to go and do a MORA survey like Caitlin has been pursuing, or maybe to basically do a very wide area slitless spectroscopic survey. Like Fresco has been surveying 120 square arc minutes over Goods South and Goods North with the F444 GRISM. And this just shows you you can end up detecting large numbers of objects, getting redshifts for large numbers of objects by looking for these various lines associated with various sources, and you can immediately get the redshifts and read them off. Here are a bunch of sources where you can essentially get redshifts from H alpha, and you can also get redshifts for a large number of sources from these other lines like Paschen alpha, Paschen beta. This GRISM data is actually very useful for getting redshifts for dusty galaxies, surprisingly enough. There's this famous HDF 850.1 that's in the Goods North survey with a star formation rate of almost maybe 1,000 solar masses a year. Basically, the redshift of this, after many years of searching, was finally derived by Fabian Walter in a Nature paper in 2012, where they detected C+ in multiple CO lines at redshift 5.18. Well, amazingly enough, we can actually get the redshift of this not simply with C++, but now with JWST, it's very easy to get the redshift of these sort of sources, because looking at this source, this source, HDF 850.1, shows a prominent H alpha line. Here's a line in the GRISM data. If you extract it, it looks like this. If you kind of smooth that and look at it a little bit, where you show less the raw data and you actually, try to smooth it a little bit, you get something that looks like this, and you see a very well detected H alpha line. This is a 13 sigma detection, and it gives the same redshift. This is the redshift 5.188. And so this is kind of amazing. You can detect a dusty object like this, but I think it's possible because we're dealing with merging objects, and with merging objects, it's very likely that things like H alpha could escape. Here's another example of a source where that looks like a very dusty source where a line is detected, and the redshift is determined as 5.58. And these aren't the only ones. There's actually a large number of these objects. I think we have a sample of at least 10 or 10 plus of these objects look very, very dusty, but we're able to get the redshifts with H alpha. And so with basically, I'll just quickly. So obviously it seems like you should extend this over wider areas and also over different redshift range. A recent effort proposal that was successful was a 356W NIRCam GRISM proposal to cover the Fresco areas by Agami, and the Miri GTO team is also adding 356 NIRCam GRISM observations over the Good South area. And so this essentially allows one to essentially search for all sorts of, to look for these various lines at all sorts of different redshifts. And essentially, if you combine 356 and 444, you can basically cover the entire redshift range and get basically complete redshift coverage. This just shows you how this is from a private communication from a proposal that Rohan wrote, which was competing with Agami, but you would add large numbers of redshifts and essentially get all the bright star-forming galaxies by just adding this data. Basically, you could add most of the dusty star-forming galaxies at redshift greater than 3.5, complete probe of the UV bright galaxies between redshift 5 and 9, and basically a complete probe of U-lorgs out to redshift 3 from all the Paschen alpha and bracket lines. So I think just having GRISM surveys over wide areas would be great. Anyway, let's just go to the summary now. Based on the NIRSpec IFU observations, we're able to detect 10 plus emission lines from O2 to sulfur 2 with just 30-minute observations for Rebels galaxies. We find these things are massive, metal-rich, and dusty. They seem to show rotation-dominated kinematics, and we're characterizing the cold gas, warm ionized gas, metal content, dust content, and kinematics for these targets. And so using the Rebel sample and GRISM observations, we're in the process of trying to draw broader, more general conclusions based upon these samples. Okay, thanks. Sorry, I guess I went a little over here.
Thank you, Rychard. Are there any questions?
No questions.
We have time. Don't worry. We have 2-3 minutes for questions.
guess that's why I decided to go over it. I just knew there weren't going to be any questions.
So there are a whole bunch of papers when NearSpec first came online and MOSFIRE about the intermediate redshift galaxies, so galaxies at redshift 3.5 or so, having a higher BPT line ratios than local galaxies, and that doesn't seem to be what you're finding. You're finding they lie along a similar sort of sequence. So they were concluding maybe that there's different chemical element abundances at those intermediate redshifts compared with local galaxies, or others were saying a different ionization parameter. What would be your conclusion now that those galaxies are intermediate and you've got high redshift galaxies that are more consistent with the local galaxies? What do you think is the resolution of that?
Well, I mean, it could be, again, who knows what's going on, but there's a lot of different results that seem to suggest that a lot of these characteristics, are basically very mass dependent. If you look at the Saunders paper that came out from some of the early Sears data, basically they were finding that a lot of the mass, once you factor out mass, then the evolution tends to be much less with cosmic time. And for example, for our sample, basically, we're getting very high metallicities, and what that might suggest is if you're in a higher metallicity regime, closer to what you might have with more massive galaxies at low redshift, you actually get fairly similar line ratios. But I mean, the one thing we haven't looked at with this whole thing is we haven't tried to figure out how this fits in with the fundamental plane and other things like this, and how these things might impact the entire analysis. But I think there's a lot of work left to be done. And but yeah, I'm not sure what I'm not sure what to say about all this. Most of the data sets I've seen people analyze haven't tended to show metallicities quite this high. So I don't know if it's because we're selecting sources that are bright in C+. I mean, all of our sources we're following up are bright in C+ and the dust continuum. So it may suggest they're definitely on the, I mean, we may be selecting galaxies which are definitely on the very high, with very high metallicities.
Okay, we have another final question.
For the V over sigma stuff, that's from the C2, I guess, measurements?
Yeah, it's from the C2. That's from the C+.
Do you have an idea of how to, is there a way to compare it to what you might get from the stellar light in some way?
Well, we've been asking for, I think Renska put in a JWST proposal last cycle where she was explicitly asking for IFU observations in order to compare the kinematics of the ionized gas with the kinematics we're getting from C+, and they didn't give us the time. So she led a proposal like basically asking, we'd like to measure kinematics based upon O3 and to compare with what we get with C+. I mean, these are different, potentially in different, phases of the ISM, and so basically they didn't give us time. But we were trying to make that point that we really want to understand how the different phases of the ISM are basically, the kinematics are similar.
Okay, let's thank Rychard again. Dale, yes.